So far we've defined work in one dimension, but let's consider the path of a particle in more than one dimension. And on this screen it looks like a two-dimensional path. And here's our particle. And what we'd like to do is define the concept of work for this type of path. Now, let's say that at this instant our particle is experiencing a force F. And the particle is being displaced by a distance ds, which is always tangent to the path. And what we'd like to do now is talk about the work done for this particle. Now, what we'd like to first say is what we're going to do is imagine that we're going to break the path down into a bunch of small intervals. And let's call this the jth point and the jth plus 1 point. Then our particle will start at j and we'll displace it delta sj to the jth plus 1 position on the path. And here, let's denote the force by fj. And now what we'd like to do is define the work for this particular section. Now, our concept of work is the force in the direction of the displacement. So what I'd like to do is I'd like to define the quantity fj, and I'll put a little parentheses upstairs, parallel lines upstairs. This is the component of the force fj in the direction of delta sj. Now, the way we denote that is we can then say that if I take the dot product of fj dot delta sj, this is the component of the force in the direction of the motion, because remember our dot product, if we call this angle theta j, is taking how much of one vector is in the direction of the other times the magnitude of that displacement. And again, when we write that component in our notation, if we call this angle theta j, we know that that's the magnitude of fj times cosine of theta j. Now, because this is the amount of force in the direction of the motion, that's how we've defined work done, and we'll symbolize the work done in taking the particle from j to j plus 1 by the symbol wj. And now, this is a scalar quantity, and when we want to find the total work, what we have to add up is from some initial point to some final point, how much work is being done in taking our particle from the initial position to the final position, and it's just the sum for all of these j's, and let's say we have n of them, of wj. And right now we're going to call this w, is just that scalar sum, and that's equal to the sum, j goes from 1 to n, of fj dot delta sj. So now we'll use the vector dot product because we already know that this is how much of the force is in the direction of the motion. However, this answer depends on how fine we broke up this path. And what we've seen many times now is that the actual work that we want, let's write this as n because it depends on the number of paths, is the limit as n goes to infinity of this sum of scalar amounts of work. Now, when we take that limit as n goes to infinity of this sum, j equals 1 to n, of fj dot delta sj, this quantity is formally what we mean by a line integral. And we denote that with a new notation. We'll denote a line from our initial to final. And it's a dot product of the force dotted into the small displacement. Now, whenever we see the dot product in an integral, that distinguishes it from a normal integral, and this is what we call a line integral. Now, again, why did we switch from our delta s's to ds's? Because when we take the limit as n goes to infinity, our grid becomes finer and finer and finer until we're shrinking down to a point where we can just talk about the differential displacement ds and the force acting on a point. And that's what our line integral is. Now, what we'll learn next is how to calculate this line integral for a number of important physical examples that occur in our interest in mechanics.